To generate frequent item sets, we'll be using the implementation of a priori algorithm from MLXtend. In task 1, we'll verify this implementation by generating frequent item sets on this dummy data manually. So we set a minimum support of 0.4, and with this minimum support for these individual items, we do not eliminate any and all our frequent item sets. We generate pairs from these individual frequent item sets and eliminate the bottom 3 as you see here. From these pairs, we generate one triplet, and from the top 3 pairs above. We prune this with the anti-monotone property in a priori principle, but this triplet still fulfills this property. However, it counts below the minimum support, and hence we do not have any triplets as our frequent item sets, and our algorithm will end here. We see that our manual output corresponds to that of MLXtend, and hence we can use MLXtend's a priori algorithm in task 2.
So for task 2, we run our algorithm implementation on 3 different datasets. Firstly, the Amazon Sports and Outdoor reviews. We first read in the dataset. There's a total of 104,000 unique products, and we perform one hot encoding for each product in each transaction. We then generate the frequent item sets, and the results can be seen in our report in this table. We show the minimum support, number of item sets, largest item set, and running time. Next, for the second dataset, we perform a similar action. We read in the dataset and generate the frequent item sets, and the results can be seen in this second table in our report. For the third dataset that we use, it is too large, and hence we need to break it down into chunks of size 10,000 each, and then we perform our algorithm on each chunk. We then concat all the frequent item sets together to get our final values. So running this algorithm on the multiple min support values, we can see our results in our report within this table. And that is all for task 2.
So for parts 3 and 4, we use 2 different data sets. Firstly, we have our retail market basket dataset, which contains anonymized transaction data from an anonymous Belgian retail store. We also have the Kaggle e-commerce dataset, which contains purchases of customers of an American e-commerce platform. So these transactions are one hot encoded and then used for frequent item set generation, just like in part 2. So then we use the generated frequent item sets to generate feature vectors. So how we do this is that we iterate through each transaction, initializing a feature vector and checking if each frequent item set is present in each transaction. This results in a binary feature where the value is true if the item set is present and false otherwise. This list of features can then be used for clustering. So the first clustering method we used was dbScan, which we evaluate using 2 metrics, silhouette coefficient and Davies-Bodied index. So we look for a high silhouette score and low Davies-Bodied index. So for dbScan, we also use the Jaccard index as our clustering metric, as it is a measure of similarity between 2 asymmetric binary vectors, making it suitable for our features. So we first use the default parameters with an epsilon of 0.5 and minimum samples of 10. So for the retail market basket dataset, initial clustering shows very poor performance with a very low silhouette score and a very high Davies-Bodied index. The same can be seen for the e-commerce dataset with a negative silhouette score and a very high Davies-Bodied index. So we need to tune epsilon and minimum samples. So we do this by using silhouette distance to estimate the ideal epsilon value. So what we do here is we sort the item set, the data set, by distance between its neighbors and generate a graph as shown here. We then zoom in to this area where the values change. And then, so for here, we can see it's between 0.2 and 0.5. And then we iterate through these epsilon values and see, look at the metrics to determine an ideal one. So here we see that somewhere between 0.3 to 0.35. And then we then vary minimum samples, iterating through these minimum samples as well. Then we also, once again, evaluate through the metrics where we found for this, the ideal combination would be 0.3 and 50. We do the same for the other data set. First, we vary epsilon, and then we vary the minimum samples, where we eventually are able to find that the optimal value for this is 2.15 and 10.
For k-means, like the dbScan, we first convert the item sets to features. However, we have one extra step, which is to convert it into a sparse matrix using CSR. And after that, we chose the frequent item set that is 30 in number, which have a minimum support of 0.02. And because there's 30 frequent item sets, we choose k, which is the n classes, to be 30 at first. And the rest of the parameters are at default. And we use the inertial, silhouette coefficient, and Davies-Bodied index to evaluate the effectiveness of k-means, and these are the results. And for part 4, we use the elbow method to see which k is the best to use. And this is the graph that we generated by testing k is from 0 to 55. And the elbow looks like it's around 10 to 30 plus. So we test the parameters for k from 25 to 35, and also have other hyperparameters such as n init, which is the number of times the K algorithm is running with the different centroid seeds. So after running all the tests, we got our results, and the best results are stated in the report.